All right, guys, I'm going to show you the poster that we made that was over uh, anaerobic respiration. So this was what we drew last class. And so let's indicate this is the 4 steps of aerobic respiration. If our cell is getting oxygen, then we're going to break down glucose utilizing glycolysis, this prep reaction, real short. Then we have the Krebs cycle, and eventually all these NADHs that we've made are going to be oxidized. And so the 4-step oxidative phosphorylation. And that provides a area of highly concentrated protons that can flow through ATP synthase and make ATP. Okay, that happens as long as there's oxygen to keep the electrons moving down the electron transport chain. However, sometimes our cells are not getting as much oxygen as they need. And so something different is going to happen now in our cells. Now, when I flip this over, okay, I'm going to change and I'm going to make my paper go up and down this way. And I'm going to split it in half because we're going to show you anaerobic processes in like animal cells, and then also yeast is going to be different. Okay, so let's indicate we have anaerobic respiration taking place. Anaerobic respiration. Oops, spelling it wrong there. Let's try that. There we go. Okay. And we're going to take a look at what happens in animal cells, like your cells, and some bacteria. Because the bacteria that can do this, we use to make yogurt. You might see on yogurt it says contains live cultures of Lactobacillus acidophilus. So they produce lactic acid, and that curdles the milk and makes it thick. It changes the proteins in the milk. That's how we're able to make yogurt using bacteria. Okay. All right. I'm going to go ahead and make a pretty good size cell. And I'm going to, since we're talking about animals, let's go ahead and put the bloodstream in there. And let's add that we're getting oxygen and C6H12O6. Okay. Now, we know that glucose is going to enter the cell, right? And we are still going to have glycolysis occur. So this is glucose. Let's put our 6 carbon atoms on there, okay? And just kind of review a little bit of glycolysis here is we end up using 2 ATP to start this process. Now I'm really going to simplify glycolysis because we drew it on the other page, okay? And we've practiced with it today. So there's lots of ways I can diagram, and you still have to know it's glycolysis. And then eventually that gets cut in half, and we end up with, this one was phosphorylated from one of the ATP, and then we're going to have one over here that was phosphorylated from the other ATP, okay? Now, this is a really important step. This step will eventually lead us to these steps that produce 4 ATP, okay? And remember, in this step, this is where we're going to get our first oxidation reduction reaction. So oil oxidation is losing. This intermediate is going to lose a proton and an electron, okay? And remember, it was picked up by the NAD+. And that's what gave us the NADH. And that happened here, and that happened over here. So I'm just going to show we get an NADH over here just to keep everything consistent, okay? Now remember, all of these buses went to an electron transport chain, okay? Now, this next part that I'm going to show you is I'm going to show you why we need the fermentation step when we don't get oxygen. So let's go ahead and let's show, here is a mitochondria. Let's put in that inner membrane and put some of those electron transport chain proteins in it, and maybe some ATP synthase, okay? Now, if you remember, we had to take off 12 hydrogens and place them on the NAD pluses and the FAD pluses. And so we made 12 of them. We made 10 NADHs. We made 2 FADH2s for every FDH2 for every, we made 1 in each of the Krebs cycle. And remember, it happens twice. So you get 2 FADH2s, okay? Now remember, they have to get oxidized here, but we might have a problem. So remember, the electrons are supposed to move down the electron transport chain. And this electron has to be removed by oxygen. Well, if the cell isn't receiving enough oxygen, then this electron can't be pulled off the electron transport chain. There's no final electron acceptor. And then this electron can't move, and this electron can't move. And remember, it's them moving which allows us to concentrate those H pluses that can then flow through ATP synthase. So if there's no O2, then what's going to happen is these electrons are going to stop moving, our protons are going to stop being concentrated, and these molecules, these coenzymes, NADH and FADH2, they can't get rid of their electrons. They can't be oxidized because there's nowhere for them to go, okay? So when there is no O2 to be the final electron acceptor, this fourth stage, oxidative phosphorylation, I just wrote number 4 there, it stops, okay? Now remember, in the Krebs cycle, or the citric acid cycle, we needed 3 NAD pluses, because remember, it's 3, 2, 1, 1. So here's the problem, is if these 12 buses, let's say we only had 12 buses, if they're all loaded up and they cannot be oxidized here to release them, then we don't have any more buses to pick up again. This needs 3 NAD pluses, and we don't have them. They're all tied up. So the Krebs cycle is going to stop as well if there's no NAD pluses. And then same with the prep reaction, because we do get an NADH produced per pyruvate. So all of these processes are going to stop, okay? And glycolysis is also going to stop if we don't have any buses to load, because they're all over here, unless we can figure out a way to free up some more NAD plus somewhere. We gotta unload these or oxidize these molecules somehow, okay, to get us some NAD plus, okay? So let's say that this reaction continues. Let's go ahead and let's show that we had some NAD plus, so we got some NADH. And here's the steps where we make ATP. I'm just gonna very simply put, remember, it's through substrate level phosphorylation, because this is oxidative phosphorylation. So the ATP is made by substrate level phosphorylation. So let's just show that we get 4 of them, okay? And then ultimately we end up with pyruvate. Okay, but now, if these are the last 2 NAD pluses that got turned into the NADHs, and all the NADHs are over here, but they can't unload, this is where glycolysis would stop, because this next reaction, we have to pull off that proton and electron to get the next molecules to get ATP, to the steps that are producing ATP. So let's go ahead and indicate the first step was glycolysis. And now that we aren't going to be able, the cell's not going to be able to, the next 3 steps, we have a different process that can occur. So let's indicate, we're going to put lactic acid fermentation is the name of the second step. Lactic acid fermentation. Okay, so here's what's going to happen, is this NADH, we are going to oxidize it. We have pyruvate that we can use. So let's show the NADH next to this pyruvate. And there's an enzyme that is going to, oxidation is losing, is going to oxidize the NADH. That means that it's going to pull off a proton and an electron. And now it's going to put it on that pyruvate. So my pyruvate is getting reduced. Actually, let's label those are pyruvates. So let's say pyruvate is reduced. And now it's not pyruvate anymore. Now it is lactic acid, or you can call it lactate. Okay? But this is not what the cell is trying to make. This isn't going to benefit the cell right now at this second because the cell isn't, it's running low on ATP. It needs ATP. But the most important part to this is after this NADH is oxidized, then that means we have regenerated. So let's indicate we have regenerated the NAD plus needed to at least keep glycolysis occurring. We won't get much ATP, but at least we'll get a net of 2. Okay. So we still get, if you want your markers, okay, so glycolysis can make NADH, and if that step can happen, then the next steps can happen, which can give us 4 ATP. Now, when all of our coenzymes, though, have been reduced to NADH, they can't be unloaded, there's no oxygen, that's when the NADH is going to be oxidized, and we're going to put that hydrogen onto this end product that we have here, pyruvate. And that makes lactic acid, but again, it regenerates the NAD+, and it happens over here as well. So we can show, might as well show it, huh? So let's show the NADH. Okay, so the NADH here in the cytoplasm. I'm running out of room. I sent it out of my cell, which isn't quite the case, but it regenerates that NAD plus for this step in glycolysis. Okay, so that's the biggest thing to know is what is the purpose of this fermentation step? It's to regenerate NAD plus to provide that for one of these earlier steps in glycolysis, so glycolysis can keep occurring and we can at least get 4 ATP. Okay. All right. Now on this last one, let's show alcohol fermentation. And actually, let's go back up here and let's put LA fermentation. Okay. And so let's do anaerobic respiration, but show what happens in yeast cells. Okay. So let's indicate yeast, and there's also some bacteria. Some people have certain types of bacteria that when they lack oxygen, they'll produce alcohol and yeast in their gut. And if you eat a very sugary meal, you're feeding them, there's not hardly any oxygen in the digestive system, so they start producing alcohol. And it's the exact same alcohol as what you would drink that would make you feel intoxicated. Okay. All right, I'm going to pause this for a second. Okay, so to continue on, I had to pause, teach a class. All right, I'm back. Anaerobic respiration, yeast, and some bacteria cells. So let's go ahead and draw a unicellular organism here. And yeast, now I know bacteria can't because they don't have mitochondria, but yeast are eukaryotic cells. They have mitochondria, and they will do all 4 processes, just like our cells do. So let's go ahead and indicate kind of the same thing that we did, is that here's an electron transport chain. And if there is no oxygen, no O2 diffusing into the cell, then the electrons can't move. And therefore, all the NADHs that are being created and FADH2s in those previous steps cannot get oxidized. So therefore, we won't move electrons, we won't be able to concentrate the protons, and ATP production will cease because they won't flow unless there's a high concentration of protons on the outside. So let's put, once again, step number 4, oxidative phosphorylation cannot happen when the cell lacks oxygen. Same with step number 3, Krebs cycle will stop, and so will the prep reaction. All of those need NAD pluses, okay? Even glycolysis needs the NAD pluses. So glycolysis can happen, and then instead of doing the prep reaction, we can do a second step, and that can at least give us some NAD pluses for glycolysis. So let's show glucose entering the cell. Let's put the first step is glycolysis. All organisms do glycolysis. It evolved very early at the beginning, whenever we have very simple cells, and glycolysis got passed on from generation to generation because those proteins that do it are coded for by DNA. And so again, that DNA gets copied. Now you have other cells in the next generation that can also perform glycolysis. All right, so let's go ahead and again, we're just going to show it very, very simple. So let's go ahead and talk about at the end of glycolysis, we end up with the pyruvates. Okay, and to make those pyruvates, we needed an NAD plus, and it would have gotten reduced to NADH. Okay, so if we made it down here, there was definitely an NAD plus getting reduced. All right, now if we have a high concentration of NADHs and FADH2s here, and they cannot be oxidized, the NADHs are not going to be able to go into the mitochondria. Okay, so these H's won't be released here. We have to have a place to release them so that we can regenerate this molecule as NAD+. For the next glucose that comes in, then glycolysis can happen. And remember, if glycolysis is happening, then we are going to get 4-ATP. Okay. So this cell would be done. Even if more glucoses came in, nothing, we would not be able to catabolize and break down the glucose, even in glycolysis, if we're out of NAD+. So if we have NADHs, if we have pyruvates, then the NADHs can be oxidized. And that means that their proton and their electron is going to go onto the pyruvate. It's not pyruvate anymore. That is, actually, let me pause for a second. I'm going to, this one's a little bit different than up here. Okay, so we had pyruvate gets turned into lactic acid. But this second part, these second steps, which is the fermentation step, in this case, it's alcohol fermentation. Alcohol fermentation. And actually, we can just leave it like that. No, we need to take off one. So there's actually a two-step process. So the pyruvates, let's indicate pyruvates. In one step, one of the carbon atoms is removed. Actually, I'm butchering this, so I'm just going to leave it like this. So it's two steps. We end up removing one of the carbon atoms as CO2. So let's show that we get CO2. All right. This molecule also then gets reduced. So NADH is getting oxidized. The pyruvate is getting reduced, is what I'm just writing here, reduced. And now it is this 2-carbon molecule, and this is ethanol or ethyl alcohol. Okay, so that is an alcohol.
Ms. Pacelli, can you please come to the main office? Ms. Pacelli, to the main office.
And again, it also happens to this pyruvate over here. So I want you to, you can show that NADH is going to lose its proton and electrons, and that regenerates NAD plus for another glucose to come in and be broken down through glycolysis. But this cell, it's not benefiting from the making of ethanol. This is not what is going to keep that cell alive. What is keeping the cell alive is that it at least can produce 4-ATP if it can regenerate. So let's show that once these are oxidized, then we now have freed up NAD for the next glucose to come in and for it to be broken down in those early reactions in glycolysis, okay? So alcohol fermentation, just like lactic acid fermentation, that step is necessary to regenerate that NAD plus. Okay. So glycolysis can continue and at least give us 4 ATP.